This example problem illustrates what we went over last time to a good extent. Draw the resonance structure of the intermediate and then product two major products in the following reaction and label them as a kinetic or thermodynamic product. So what we've been going over is 1,2 and 1,4 additions to 1,3 dienes. And a lot of times I'm kind of old school. Let me fix that up for the new school people. So that's just our template. That's the smallest little motif where we see this recreated over and over. I don't have 1,3-butadiene. I have this cyclopentane thing, but do you see a 1,3-butadiene built inside? 1, 2, 3. There it is. And it's good to see that. And when you see something like this, one reason I go over this is where do you want to add that first hydrogen? Now granted, one hydrogen, one hydrogen, one hydrogen, no hydrogens. This is the poor area, but you want to add that first hydrogen right where the number 1 is. And of course, there's already one there. Those electrons jump down, pull out our resonance arrows. So that can either hit there or there. There's our two products. Which one do we want to say is the kinetic and which one do we want to say is the thermodynamic? So I just have these memorized that the 1,2 is the kinetic and the 1,4 is the thermodynamic. What if you didn't have that memorized? Could theory tell you which is which? In the energy diagram, the kinetic was at a lower energy, and we started this chapter off talking about the hydrogenations of different alkenes. And the more stable an alkene was, the lower its delta H of hydrogenation. And if we just go back to our regular old butadiene, hope that shows up on the camera. And this was thermodynamically more stable because the double bond is more substituted. That was Zeta's rule. And you can see, well, this almost looks more substituted there, but I don't want to get twisted up on that.
Can you explain why we added the H to the first carbon?
Good question. Why did we add the hydrogen to this carbon? Well, I like to invoke Makarnikov addition, and these three are all tied. But if we think about our 1,3-butadiene template, we have to add it here. And so one reason I bring that up, if you add it here, that might mess this whole thing up. Any other questions?
When you chose to number them, was it just like
Well, I chose to number this not for any naming, that's for sure. Yeah, I just numbered this because we've been going over the 1,2 and the 1,4 additions, which is a common thing with a conjugated double bond. So here's the conjugated double bond, and I could have started one here, but since there's no hydrogens and I want to invoke Makarnikov regioselectivity, that'll keep myself and students from getting tangled up in something that may not work right. And if you look at example problems, they're going to add the first hydrogen here. Yeah, going back to that previous question, we've been doing 1,3-butadiene because it's the simplest to start out with, but then we can put any old conjugated diene through that addition. Beginning of this section, we talked about the allylic carbocation and how it's stabilized. And now we're going to look at this thing called an allylic radical. And so remember, you want half arrows, and you can move one electron around at a time. That's what a radical is. A free radical. And here we left out the methyl radical, but we have a primary, a secondary, and a tertiary. And this thing is saying a primary allylic is more stable than a tertiary. Substitution at the allylic position competes with addition to double bond. To encourage substitution, use a low concentration of reagent with light, heat, or peroxide to initiate the radical formation. We can go back to our free radical halogenation mechanism. The first step is an initiation step. Here's Br2, some UV light. Here's two radicals. So here's a double bond, and an allylic position is a carbon that's bonded to an sp2 carbon. So there is an allylic hydrogens, and there's actually two. So this abstracts a hydrogen with one electron, giving us HBr, leaving that free radical. And so practice with our free radical arrows goes something like this: half arrow, got a leftover electron, half arrow. And then there's actually two things that can happen. A termination step, a bromine radical could hit here or there, or this propagation step. Here's Br2, one electron, and bromine atom hook up with that one electron. The other electron in this sigma bond leaves with that bromide. So this would clearly be a propagation step. And with this symmetric molecule, we can't tell if the bromine went here or there because it looks the same. All right, here's the NBS I was trying to get everyone to remember. So we've seen this before. Chemists like to use this because we can get a very low and constant concentration of Br2. We put this in with our substrate that we want to brominate, probably UV light, and then we can slowly titrate, add HBr, and each time we add a molecule of this, we get a molecule of Br2. And so once this thing does its thing, we have this succinimide here, and it says, and it prevents HBr addition across the double bond, because we should be able to react HBr with this. This is a base. So as long as we have some of this, when we add HBr, it makes our bromine, and then I don't know how we stop this from premature reacting. We're not going to worry about that, but there's not going to be any of this around to add across the double bond. So we get a nice bromination. So here's our Alli system, very similar to the Alli cation. This is the Alli radical and the Alli anion. The three p orbitals of the Alli system are parallel to each other, so there's extended overlap between all three carbons. And here we see these are basically bond dissociation energies. We take this bond apart homolytically, takes this much energy. So here's our primary, here's our secondary, here's our tertiary, and here is a allylic, and it has the lowest energy. So now we'll look at the bromination again. It abstracts a hydrogen to form HBr, creates a radical right here. This electron jumps on carbon. The other electron hooks up with bromine radical, make HBr. And here is the resonance stabilized allylic radical. And notice the similarity here. This looks kind of similar to a 1-2 addition where, I don't know, the double bond hasn't moved. Here's the double bond has moved. And unlike that first example with the ring that was so symmetric, we're going to get a mixture of two products. This thing that has the double bond in the middle, and this thing that has the double bond on the end. During propagation, an allylic radical is formed, stabilized by resonance. Either radical can form the final product, and that's why we see two different products here. And some more history about this reagent, succinic acid. If you take biochemistry, you probably run into that. Here is succinimide, and here is N-bromosucciniamide. This is the NBS. So you buy a jar of this, put it in your flask. So here's the overall bromination reaction. This thing here comes from reacting NBS with HBr. Get this in small amounts. And this gets kind of soaked up so it doesn't react with a double bond. That's what that one slide was trying to tell us. One resonance form shows the radical electron on C1 with a pi bond between C1 and C2. The other resonance form shows the radical on C3, and the pi bond over here. Of course, nature, we really have some hybrid, this combined representation. So if we look at the molecular orbitals, no resonance form has an independent existence. We think of this all being kind of pi bonded. And so it's like we have two bonding pi bonds, and here is a anti-bonding, which is the allylic radical. The radical electron occupies the non-bonding molecular orbital. And here we see the allylic cation that we looked at. We have 2 pi electrons, and when they're in the bonding molecular orbital, our orbital diagram looks like that. And here's the allylic. We pull off that hydrogen and 1 electron, and all of a sudden we say we have this extra electron. And here's something we haven't looked at, the allyanion. We'll say that for later. So substitution reactions can occur in the allylic position if we put a halide or a tosylate. Allylic halides and tolulates react quickly by an SN2 mechanism. Probably the fastest substrate for an SN2 mechanism, and it's stabilized through conjugation with the p orbitals of the pi bond. This transition state has a lower activation energy and explains the enhanced reactivity of an allylic species. So here's just a primary alky halide. The nucleophile comes there. Here's this concerted reaction, and notice the inversion of the stereocenter. It's not really a stereocenter because we have 2 groups the same, but you can see the Walden inversion, which I always like to make a joke and call it Waldo inversion. Now here we have the double bond, and in the transition state, we get this nice overlap. So an allybromide reacts quicker. Allylic halides and tosylates react with Grignards and organolithiums. Here's an organolithium. Here's straight up allybromide. And so you can think about it like this. 2 unshared pure electrons, strongest base known to mankind. Better keep any acidic protons away, and this bromine's gonna leave and you stick on a methyl group. So whenever you can form a new carbon-carbon bond, chemists appreciate that. Last thing we're going to look at is this thing called a Diels-Alder reaction, named after Otto Diels and Kurt Alder. They got a Nobel Prize in 1950, 75 years ago. The reaction is between a diene and an electron-deficient alkene, which we call the dienephile. And we get a 6-membered ring out of it with a doubled bond. The Diels-Alder is also called a 4+2 cycloaddition because a ring is formed by the interactions of 4 pi electrons of the alkene with the 2 pi electrons of the dienephile. Now I get to make my favorite joke. W, this is not tungsten. Everybody knows W is tungsten on the periodic table. We use W to mean withdrawing, electron withdrawing group, like an oxygen or maybe a chlorine or something that's electronegative, something that withdraws electrons. And it says a 1-step concerted reaction. Diene reacts with an electron-poor alkene. It's electron-poor because it's got this electron withdrawing group to give cyclohexene or a cyclohexene diene rings. So in short, if you can imagine this thing just kind of forming, there's our cyclohexene, but a pair of electrons jump there to form that bond, a pair of electrons jump there to form that bond, that one jumps there. That's how you want to visualize this. And then if you can do that, it should be fairly straightforward. So it's like the 1,3-butadiene. We can spice it up and have a bunch of other stuff going on. But here you see the 1,3-butadiene motif or picture of it. So here's our alkene. So this thing here is a electron withdrawing group. So here's the diene and the dienephile. And once again, we want to imagine a 6-membered ring where this becomes on the other side and then the double bond moves there. So now we got something crazy going on. We still have this 1, 2, 3, like a 1,3 diene. And here you can see the 6-membered ring. And since we have a triple bond here, once again, we want to imagine the ring forming there and one of those electrons jumping there. Excuse me, the pair of 2 electrons jumping there, and that one jumping there, and there's the 6-membered ring. And this thing's still there, so we kind of push it up like that, or nature does that for us. So here we see a bicyclic system. Once again, you want to imagine your 6-membered ring right here. These electrons jump there, form that bond. Pair of electrons jump there, form that double bond. This pair jumps out there, forming this bond there. Now the first simple problem we looked at, we didn't have to think about this, and that is stereochemical requirements. Well, we looked at this the other day. It says the diene must be in the C-cis conformation. Diene C1 and C4 p orbitals must overlap with the dienophile's p orbitals to form new sigma bonds. Both sigma bonds are on same face of the diene. So we say this is a syn event, syn stereochemistry. So here's our diene, and here's our dienophile. So forms to the same side, and so these blue lines are the new sigma bonds, and here's the double bond. So there's the double bonds of the diene. That thing has a double bond. So this rings a little on its side compared to the other slides. So it has to be in this position. Can't be in this position, but we learned from the other day that at room temperature, this thing's spinning around and it spends plenty of time in that configuration. So here's a collection of dienes. I would call these all a 1,3 diene. They're all conjugated double bonds. And it says here, cyclopentadiene undergoes the Diels-Alder reaction readily because of its fixed S-cis conformation. That's this thing. It's locked into that magic position. This thing can spin. This thing can spin. These all can spin. When the diene is sterically hindered, the reaction slows down, even though the conformation can be S-cis. And this thing here is locked in what we would call the S-trans. That's an S-trans diene that cannot undergo the Diels-Alder reaction. I'm going to end here.